is going to be video notes 2. And we're continuing sex-linked traits, but these are going to be some example problems, okay? So I did type this up because otherwise it was going to get kind of messy. So if you have to stop the video and write all this stuff down, that's fine. I need you to write all that down, okay? So just so you have these problems, okay? First one, determine the sex and eye color of the following fruit flies. No need for a question mark. R is red eyes, little r is white eyes. So again, the first thing you would see here is XX gives us female, and big R, little r gives us, well, this is dominant over this, so that is going to be a female with red eyes. And then we have XY, which is male, and it has a little r right there, so that means white eyes. And so just to remind you, there is no gene for eye color on the Y chromosome right here. That's just, there's nothing there because this is an X-linked gene, okay? So all of the problems here that we're talking about are going to be X-linked, okay? Maybe I should say up in the corner, X-linked problems, okay? All right, next one. So a woman who is a carrier, okay, so we did not talk about carrier yet, but just keep on with me here. A woman who is a carrier of the hemophilia gene marries a man who is normal for the trait. Hemophilia is an X-linked and it's recessive, okay? So let's go back to carrier. Carrier just means somebody who is heterozygous. I will use this. You should know carrier is heterozygous because basically being a carrier means that you carry the allele for the gene or for the disease or for the trait, whatever we're talking about, but you do not have that disease or that trait. So for example, she is XX, but it says she is a carrier, which means she's heterozygous. So she has the little r. Remember, we also said that this trait is recessive. So she has a little r, but she doesn't have 2. She only has 1. So she has a big R, little r. So she has this. She carries the allele, but she does not have hemophilia herself, okay? So, and then marries a man who is normal for the trait. Okay, so let's write the key over here. So the key is just going to be, this is like normal blood clotting. If you remember, hemophilia is blood clotting disorder, hemophilia, okay? So that's still our key. And then we have to do the parents. So the parents are going to be X. We already wrote the woman's, right? She's a carrier for it, but doesn't have the disease herself. And he is normal, so he has X big R Y. What goes here? Nothing. Okay, I'm even gonna just erase that so you don't copy that down. All right, so now we have the parents. All we're gonna do is put those 2 parents in a Punnett square. Bam. Let's make the Punnett square. Whoa. Whoa, okay, that's better. X, big R, Y. So if we fill this in, you don't need to watch me do this. Yeah, just do it yourself to see if you know what's going on. And you can check me for mistakes. Okay, so there's our Punnett square. Now we got to answer these 2 questions. Okay, what is the probability of having a child with hemophilia? So what we're going to do is we're going to look in all of these squares because we're just looking for any child, boy or girl. With hemophilia, this one, no hemophilia. This one, nope, no hemophilia. This one, not hemophilia. This one, winner. Okay, or not really. Has hemophilia. Okay, so what's probability of having a child with it? 25%, right? Because we saw that 1 out of 4 did. Okay, now here's a little bit trickier question. What is the probability that if they have a son, okay, if they have a son? So now we're only going to look at the boys. So I'm going to go back to this. I'm going to erase that real quick. Erase these little guys. Oops. Oops. Can I erase? Ooh, yeah, I got it. Okay. So now we're going to look for only at the boys. We're going to look at these two. And out of those two, one of them has hemophilia. So we are going to say 50% is our answer, right? Because we had 1 out of 2 in that one. Cool. So you gotta be able to tell that these are slightly different questions. Okay. All right. Let's go to the last example problem. All right. Red-green color blindness is caused by an X-linked recessive allele. So just like the last question, color blindness and hemophilia are the same type of inheritance. So we can already start making our key. Because if we know color blindness is recessive, we have to put colorblind down here. That's how you get that trait. It's recessive. So this will just say normal vision. Okay. Well, let's get to the parents. A colorblind man. So So the man is XY. And so if he's colorblind, he needs one of these. So right there. What goes here? Nada. Nothing goes there because it's X-linked. It's only on the X chromosome. All right, then the other parent, normal vision, whose father was colorblind. I like this. You got to get a little bit clever. So woman with normal vision. So we know she has one of these big R's. However, since her dad was colorblind, so let's draw her dad up here. So X, little r, Y, right? Because he was colorblind, so this is what he had to be. So if he has a daughter, he has to give her this one. Dads don't give daughters Ys, right? Well, you know what? That's getting messy. So he has to give her this one, so that means she has to be this X big R, X little r. That is her genotype. Okay? So those are the two parents. Let's make a Punnett square with the two parents. Oh, that was a pretty good square, guys. My squares are getting better. Kind of. I mean, I know it's not attached down there, but it's not bad. All right, there it is. Okay, so now let's read these two questions. What is the probability that their child will have color blindness? Okay, so again, we're just looking for any of their children. So we're looking in all of the 4 squares. And again, let me get a different color and be like, does this one have it? No. Does this one have color blindness? No. Does this one? Yes. Does this one? Yes. So the probability of getting color blindness or having their child having it is 50%. Okay, now let's do the next one. Let me erase these. Okay, what is the probability that their child will have color blindness and be a girl? Okay, so now we want 2 things. So we are going to have to multiply 2 probabilities together. So what is the probability that their child has color blindness? Well, we just said 2 out of the 4, right? These 2 have color blindness. So we can say 2 out of 4 have it, or 1/2. And then we're going to multiply that by what is the probability, and a girl. So, sorry, this probability is 1/2, and the probability of having a girl is also 1/2, right? So, because there's 2 of these are girls, these are boys. So again, 2 out of 4 are girls. And so if you go 2 times 2 is 4, and 4 times 4 is 16. This is just 1/4, or 25%, right? And that makes sense because if we just look at the Punnett square, we can see, no, erase. If we look at the Punnett square, we can see that one of them, 1 out of 4, or 25%, is colorblind and is colorblind and is a girl. Okay, so that's another way of doing that. All right, guys, so with these problems, you should be able to manipulate all of these different alleles, throw them into Punnett squares, and be able to solve any problems that I throw at you. Okay, so make sure you understand every aspect of this, and when you do the worksheet, you're actually doing them correctly with the correct notations. Okay, I know it gets confusing with the X's and the Y's and the letters that we need for the genes, but we got to stick to this. Okay. All right. Thank you very much.